Hey, so in this video I want to talk about a least squares fitting for some data points. It's a really cool topic, so just trying to make sure I get my camera on here right. So least squares fitting. So what does that actually mean? Let's say that like you have bunch of data points or some equations. So you have some equations here that you plug a value in and you get some result out here. Okay, so you got a couple data points here, here, a lot of points, a couple out here, couple out here, and you want to fit a line that approximates this data the best way. Well, the best way to get that line, I mean, this is probably out here, probably not a good point. Out here, probably not a good point. So best line is probably like something like this right here, right? A line through there. And so least squares fitting accomplishes this because you have an overdetermined system. So that means you have more equations than you know what to do with. A good example here, let's start out, let's say we have a couple of equations. So let's say we've got a line, we've got some data like this, got point at, let's go 0, 1, 2, 3, 6, 1 here, and then we've got another point at, let's go 1 here, and another point right here. Why not? We'll do that. So no straight line goes through these 3 points, and we're asking to find two numbers, C and D, that go through these points through a straight line. So we want B equals C plus DT. So the way that we get started with this is we write down our equations first. So we got C plus D, and I'm going to put the labels on these. So we have 0, 6, and 1, 0, and 2, 0. So for the first equation, we got C plus D times 0 equals 6. And then we have C for equation number 2 plus D times 1 equals 0. And then for number 3, we have C plus D times 2 equals 0. It's got 3 equations and 2 variables. All right. So if we were to take this and put it in a matrix form, we end up with 1, 1, 1, 0, 1, 2 times C, D equals 6, 0, 0. Okay. So right now this is overdetermined, right? If this is our matrix A, and this is our vector X, and this is our solution vector B, right now the number of rows is greater than the number of columns. So we have M is greater than N. So it's overdetermined. And it's not solvable. Well, it appears that way. The problem is this type of problem where you have more data than you know what to do with happens all the time. In my case, it happened when we were trying to solve some equations for the picture. We had a camera matrix that we're using to approximate points in a 3D space, and we had so many points we didn't know what to do with them that we had to come up with an approximation of the position of this thing that was occupying all these 3D points because there were so many of them. We want to get the approximate position. So least squares gives us a way to do that. The way that we can minimize the error, just to get started here, we have if we take b, we subtract a x, we're left with the air. And we want to minimize that, right? So now if you're familiar with projections, you know that we can use the projection P, which is defined as AX. And this should be just X here, right? We can use the projection P equals A X hat. We can get an approximate, if the air is small, we can use this as an approximation of what AX should be. And right now, the way this is set up, we wouldn't be able to solve this equation, but if we multiply by the transpose of A, then if we do the transpose of A, let me just move this over here. Transpose of A, so A equals 1, 1, 1, 0, 1, 2. That means that A transpose equals 1, 0, 1, 1, 1, 2. So this is a 2 by 3. This is a 3 by 3. And if we go back to this equation, this is a 2 by 1. So if we take our equation, we go A transpose A X, and we have to do the same to B, A transpose B. That gives us 1, 1, 1, 0, 1, 2 times 1, 1, 1, 0, 1, 2, and C, D equals 1, 1, 1, 0, 1, 2, 6, 0, 0. You can see that. Okay. All right. Now, if we go through and we solve this out, what we're going to end up with is we've got to do this matrix multiplication. And if you don't know how to do matrix multiplication, I don't think it makes sense for me to go through all that for you right now. I'm just going to tell you that whenever you do this type of equation, you end up with what's referred to as the dot product matrix. So that's just going to be M, and in our equation we have B equals C plus DT. It's a symmetric matrix, and you end up with TI, sum of TI, TI, and the sum of TI squared here. A transpose A equals that. So for our matrix, the matrix is gonna what this comes out to be is 3, 3, 3, 5 times C D equals now we know this bottom one's going to be 0 here because these guys. Let's do this first one. So what do we get? 6. And then do this guy. What do you get? 0. So if you end up solving this, you'll come to find out that C equals 5 and D equals -3. So we get B equals 5 minus 3t. Okay, so what does that line actually look like on here? It's kind of something like hard to draw. Kind of like goes right in here. It's gonna look like that. And then these are our errors. So I hope that helps. Just a quick video to show you that if you multiply by the transpose, you can get this in a form that's solvable. It's really useful, and you never feel intimidated if you have too many equations. That's a good thing. You can get an approximate answer, and a lot of times in engineering, that's what you have. You have too much data, and you gotta use averages. Yep, that's a quick video.